So in section 3.4, we're going to move on to another attribute of all of our kinds of functions, actually, and it's called concavity. Concavity talks about whether a graph is opening in a certain direction. So in kind of a verbal description sort of way, things that open up, think about your normal graph of a parabola, would be concave up because it's opening upward. And if you turned your parabola upside down so that it was pointing downward, we would call that concave down. Now, not all of our graphs have that definite sort of a picture to them. It might look more like half of a parabola. But it's still talking about how the shape of the graph is changing. Okay, that's what concavity does. It also mentions that we're going to look at the second derivative test as we look at this section. And the second derivative test talks about using the second derivative instead of the first derivative to decide if a function is increasing, has a relative max or min. Okay, so it still tells us information that we were looking at in section 3.3, about relative max and min, but it does it using the second derivative instead of the first derivative. So we're going to take a look first at concavity. For a function f that is differentiable on the interval I, the graph of f is concave up if the derivative is increasing. No, it doesn't say the derivative is positive. That's what we did before. It says the derivative is increasing. So we'll learn real quick that that actually corresponds to how do we know if something is increasing? Well, we took the derivative and we found out where it was positive and negative, right? And if you take the derivative of the derivative, that's otherwise known as the second derivative. So we're going to be finding second derivatives in this section. Likewise, it's concave down if the derivative is decreasing. So I'm going to write it in here, although it'll be written in a minute here in a nicer fashion. This is telling you that the second derivative is positive or the second derivative is negative. That's what it really means. If your derivative is increasing, then your second derivative is positive. If your derivative is decreasing, your second derivative is negative. And we get that by pulling back into what we just did in the last section. How do we find out if something's increasing or decreasing? We take the derivative and we look whether it's positive or negative. So if we put it all together in a nicer fashion, you get the test for concavity, theorem 3.7. Suppose that the second derivative exists. If the second derivative is positive, it's concave up. And if the second derivative is negative, it's concave down. And it's always on an interval, and that interval is an open interval that we're looking at things on because we're always talking about an interval, not at the endpoints themselves. Most of our intervals are going to be the whole number line. We're not looking at pieces unless we're looking at trig functions typically. Anyway. So just like with the last section, you're going to enjoy taking these derivatives a bit more because they're usually pretty simple. If things get too crazy and too messy, that the derivatives become difficult to find, it becomes very difficult to decide, is it increasing, decreasing, concave up, concave down? So we start out with things that look like this. Your favorite, polynomials. I know they're my favorite, right? Because they're very straightforward. So what we're going to do, directions say, to determine where the graph is concave up, concave down. Okay? So what does that mean? Well, if we're wanting to find where it's concave up and concave down, it means we're going to do the same thing we did in the last section, but we're going to do it with the second derivative now. So we're going to take the second derivative instead of just the first derivative. And we're going to set it equal to 0, and we're going to find some test points, and we're going to set up a number line, and we're going to put it back into the second derivative, and we're going to say, is it positive? Is it negative? It feels just like the last section, but you do this one extra step at the beginning where it's taking the second derivative. So what is the first derivative of this function? Okay, everybody agree? All easy to do, right? Yeah. And then we just do it again. We take the second derivative. So what's the second derivative? 12x squared minus 12. We're all good, right? Okay, so now we're at the point where we did the same, we're going to do the same thing we did back in section 3.3. We have an equation now that we're going to set equal to 0 and solve. So setting it equal to 0. It is quadratic, so if you wanted to factor and so forth, you could do that. But it also doesn't have a linear term, right? It's not 12x squared plus x plus 12, right? It doesn't have that form. It doesn't have 3 components. So this one solves very nicely simply by doing so directly, if you'd like. So I'll shift my 12 to the other side. I can divide by my 12. So I have x squared is equal to 1. We do need to remember that when we take the square root that we put a plus or minus on there. That's the one caveat to doing so. If you were to think about this from a factoring perspective, you can pull your 12 out. You'd have x squared minus 1. It's not a very good squared. And that's set equal to 0. And then you would be able to factor x minus 1, x plus 1, blah. And then you set them equal to 0. So you can either do it from a factoring perspective, and a lot of your functions you'll need to factor, right? You don't have them set up like this one. But if you can solve them directly, you're welcome to do so as well. Either way, you find out that x is equal to positive and negative 1. And over here is the same because, of course, the square root of 1 is 1. Okay, pretty good? So we have 2 points. They're not called critical points at this point. That's something that was specific to first derivatives. But they do create the breaks on our number line. So we're going to draw our number line with those locations marked, -1 and 1. And if we were doing trig functions, which we probably will when we come back to class in a week or so, we might have an interval that's confined, right, where we stopped and started at specific locations. Here we don't. So we pick numbers in these intervals. Y'all are really good at doing this, so pick me some numbers. -2, 0, and 2. And if you don't like those numbers and you want to be more creative, go for it. Okay? The remembering thing here, though, is that we want to put them into the location where we got the equal zeros, right? The second derivative. So we're going to put those numbers into the second derivative. Now, this one we might be able to do just in our heads, and if so, that's great. If you want to be able to write a bit more down, that's fine too. If you want to grab your calculator, you can do it. Doesn't matter. But we need to take this -2 and we need to evaluate it into this function. So -2 squared is 4. 4 times 12 would be 48, and 48, so we have 48 at the beginning. I'll write that down. We have 48 minus my 12 now, 36. And in particular, it's positive, right? So we get a positive when we do that. 0 is lovely. When we put 0 in, it cancels everything at the beginning, leaving me with -12, which is negative. And just like when I put in -2, when I put in 2, because I'm squaring it, I get the exact same 48 minus 12 at the end, which is positive. Okay, again, if I'm mushing through this so fast that you're like, I don't know what she just did, just write it out. Show the parts that you need to plug in, grab your calculator and let them do it. I think you guys are probably okay. So nobody's complaining it out loud anyway, so we're going to keep moving. The difference to remember here is that the positives, negatives, positive don't talk about increasing, decreasing, because we're using the second derivative. Second derivative talks about concavity. So in a very real sense, I described for you before, you can kind of imagine parabolas, right? Parabolas that open up, parabolas that open down. So in some sort of sense, we have this shape going on, right? Positive means it's a parabola opening up image anyway. Negatives means it's a parabola opening down kind of image. So when we're looking at this in terms of concavity, what is the first concavity we see? It's up. It's concave up. And it's concave up from negative infinity until -1. And then it stops being concave up for a portion of time, and then we pick back up over here at the number 1, and it's concave up from 1 to infinity. And then sandwiched in between there, it's concave down. So it's concave down from -1 to 1. And that is, I got a label in part C, but that's the end of this particular problem. We're trying to decide where it's concave up, where it's concave down. Make sense? We're going to stop there for today. Have a great fall break, guys.